Hello my friends, and welcome to part 2 of this implementation where we're going to build together the convolutional neural network, and more specifically the whole architecture of this new artificial neural network. Alright, so it's actually going to start the same as with our artificial neural network, because a convolutional neural network is still a sequence of layers. Therefore, we're going to initialize here our CNN with the same class, which remember is a sequential class. And that's our first step, where we're going to not only call that sequential class, but mostly create that CNN variable, which will represent exactly this convolutional neural network. And the CNN variable will be created once again as an instance of that sequential class, which allows to create an artificial neural network as a sequence of layers. So now, remember how we can get access to this class? Well, first we need to call TensorFlow, which has the shortcut TF, from which we're going to call the keras library, from which we're going to get access to the models module, and from which we're going to call that sequential class. So exactly the same as before, and this initializes indeed our CNN as a sequence of layers as opposed to a computational graph. Great, and now step by step we're going to use this add method to add the different layers, whether they are convolutional layers or fully connected layers, and in the end the output layer. So we're going to use successively now the add method, starting with step 1, convolution. And so now in a new code cell, well, first we'll take our CNN object, our convolutional neural network, from which we're going to call, of course, the add method to add our very first convolutional layer. Alright, so what we want to add right now is, of course, a convolutional layer, and once again this convolutional layer will be an object of a certain class, which is the conv2D class. And this class, just as the dense class, which allows to build a fully connected layer, belongs to the same module, which is a layers module from the keras library, from this time TensorFlow, since TensorFlow 2.0. So first we're going to get TensorFlow, from which we're going to get access to the keras library, from which we're going to get access to the layers module, and there we go, from which we're going to call that conv2D, there we go, class. Conv2D class, then we add some parentheses, of course, because that's a class, and inside we have to input 3 important parameters, which are the filters, which basically is the number of feature detectors you want to apply to your images, to detect features, and these are indeed also called filters or kernels. Right? If we scroll down here, actually you have all the info of these parameters, right? Arguments, filters, the number of output filters in the convolution. Well, basically that's the feature detectors. So that's our first argument. Then we will also specify a kernel size, and actually I've prepared some slides that I made to show you. So basically this is the filter, and this filters parameter will tell us how many feature detectors we want, how many filters we want. And the kernel size is exactly, the size of that feature detector, meaning the number of rows, which is also the number of columns, because it is usually a squared array, So, for example, if we choose a size of 3, which is actually the size we're going to choose, well, that means that the size of our feature detector will be 3 by 3, okay? As simple as that. And then we have some other arguments, but no worries, we'll just keep the default value for the rest of them, because that will be just fine. However, of course, we're not going to keep the default value of that activation parameter, which corresponds, of course, to the activation function, because indeed, on a general rule, as long as we haven't reached the output layer, we rather want to get a rectifier activation function. And therefore, for this one, activation, we're going to choose once again the relu parameter's name, which corresponds to the rectifier activation function. And finally, we have one last argument we have to input, and which is not displayed here because that's hidden by this one, but which you can actually see here. That's the input shape. When you add your very first layer, whether it is a convolutional layer or a dense layer, well, you have to specify the input shape of your inputs. And here, since we're working with colored images, therefore in 3 dimensions, corresponding to the RGB code of colors. And since we actually resized in part 1 our images down to 64 by 64, well, the input shape of our images will be 64, 64, and 3. And if we were working with black and white images, here we would have 1 instead of 3. But we're working with colored images, and therefore that's what will be our input shape, 64, 64, and 3. All right, and that's the essential parameters that we have to enter. So there we go, let's enter them, starting with the filters parameter. There we go. And now the question is, well, how many feature detectors we want? Well, we're just going to go for a classic architecture. You can find many architectures of convolutional neural networks online. We're going to choose a classic one, which I of course tried on our images and which turns out to work very well. And that architecture consists of having 32 filters in that first convolutional layer and then another 32 filters in that second convolutional layer. All right, so let's just choose here filters equals 32, and feel free, of course, to choose another parameter value. I remind that this is an artist's job. You're free to experiment any architecture you'd like, and you might probably get some better results than the ones we're about to get in the end. All right, so filters equal 32, that's for the first parameter. And now for the second parameter, as we said, it is going to be the kernel underscore size, this one, and as we said, we want a 3 by 3 dimensions, and we only have to specify 3. And then, as we said, we want to make sure that we have a rectifier activation function. So here, for this new activation parameter, we're going to choose, in quotes, well, the ReLU activation function, exactly the same as before. And finally, for that last parameter, we have to specify the input shape of our images, which we have to enter in a pair of square brackets. And there we go. We resized our images to have the 64 by 64 dimensions. And since we're working with colored images, we have to add here 3 instead of 1. All right, that's our input shape, and that's it. This adds the convolutional layer to your CNN so far initialized as a sequence of layers. Good. So now we can move on to step 2. Pooling. So let's create a new code cell, and this consists of course of applying pooling, and more specifically we're going to apply max pooling, just as you saw in the intuition lectures. All right, so once again we need to take our CNN object, from which we're going to call now a new method. But is that really new? According to you, do we have to call the add method again? Well, yes we do. Actually, we're adding the pooling layers to our convolutional layer, as the next step in the sequence of layers. So there we go, we call the add method once again, and then inside, well, that max pooling layer will once again be created as an object, as an instance of a certain class, which is called the max pool 2D class. And this class belongs to the same module as before, the layers module. So there we go, we're actually going to take this, I'm going to copy this, paste that right here, and then instead of taking the conv2D class, we're going to take this time the max pool 2D class. Perfect. And inside we have to specify 2 essential arguments, which are the pool size. So let me show you what this corresponds to. So this is the whole convolutional process, with the feature detector applied to the input image, resulting in having that created feature map. All right. So that's all this, and there we go. Now we move on to step 2. So we have our feature map, which is the result of our previous convolution, and we apply max pooling to obtain this pooled feature map, that same feature map of the convolutional layer after we apply max pooling. And when we do this, we have this little frame here that will get the maximum pixel of the 4 cells inside, the 4 pixels inside. And that pool size parameter, which we're about to enter here, is exactly the size of that frame, which is once again a square. So we only have to specify the width, or the height. So basically here in this example, 2. Okay. And well, speaking of 2, that's exactly the pool size which we're going to choose, and which is the one I recommend to work with when applying max pooling. Okay. Then let's see, the other parameter that is important is the strides. Okay, so interesting. Let's have a look at our slides once again. So I'm going to move to the next slide here, and let's see by which number of pixels is this frame shifted to the right. Let's see. All right, so it is actually shifted by 2 pixels. Instead of going from this frame to that frame, which would be a slide of 1, well, we went directly from this frame to that one. Okay, and this makes sense when applying max pooling because we only want to get the maximum of each square here of pixels, right? So the recommended slide once again is 2. That indeed we're sliding 2 by 2 pixels. And when we reach, that border of the feature map here, with extra empty cells here, well, you can actually choose 2 different ways, and that corresponds to that parameter, which is the padding. The default value is valid, but the other value is same. And well, the difference is that, with a valid padding, you will just ignore the other 2 cells here. And with the same padding, you will just add an extra column with just fake pixels that are equal to 0. But don't worry too much about this padding. I tried actually with the 2 values. This doesn't change anything in the final result. And so I just recommend to keep the default value. But the slide is important, and now we're sliding 2 by 2. Okay? So let's do this. Let's enter our parameters for that max pool 2D class. The first one is, as we said, the pool size. There we go. And we want to have, exactly as in the slide, a 2 by 2 frame, which we only have to specify with the parameter input 2. And then the second argument is the strides, the essential one. And we want to shift that frame every 2 pixels, and therefore we're going to choose a stride of 2. All right, and that applies successfully max pooling. As simple as that. And you can just copy paste this line whenever you want to apply max pooling to your CNN. And actually, speaking of which, well, now we want to add a second convolutional layer, and admire how I'm going to do this so efficiently. So first I'm going to create a new code cell, then I'm going to take that cell, copy it, then paste it right here. Then for the pooling, take that cell, copy it, then paste it right below. And now, according to you, do we have to change something here, or can we leave it this way? Well, we can't leave it this way actually. We just need to remove that input shape parameter, because this one is entered only when you add your very first layer, to automatically connect that first layer to the input layer, which automatically adds the input layer. But here we are already with our second convolutional layer, so that's all good. We can just remove it. Good, and now, perfect, all this adds a second convolutional layer with max pooling applied. And we can now move on to step 3, flattening, which will consist of course, flattening the result of all these convolutions and poolings into a one-dimensional vector, which will become the input of a future fully connected neural network, just as we built in the previous section. All right, so let's do this. Let's implement that step 3 flattening. And well, as usual, we need to take our CNN object, from which we're going to call the add method once again, because the way we're going to create that flattening layer is once again by creating an instance of a certain class, and that certain class is the flatten class. And Keras will automatically understand that it is the result of all these convolutions and poolings that will be flattened into this one-dimensional vector. So the only thing we have to do is just to specify that we want to apply flattening, and to do this we need to call once again the layers module by the Keras library by TensorFlow, from which we're going to call this time that flatten class. And good news, this class actually doesn't need to take anything as parameters. All right, so this simply implements step 3 flattening, and we can directly move on to step 4 full connection. All right, so now it's your turn. You can actually do it yourself. So I would like you to please press pause on the video, because we are in the exact same situation as before, building a fully connected neural network. So you know exactly how to do this. I would like you to add a new fully connected layer to that flattened layer, which is now nothing else than a one-dimensional vector that will become the input of a fully connected neural network. So do this first, and we'll implement the solution in a few seconds. Good. All right, let's do this. So you know exactly how to do this. First, we create a new code cell. Then we take, once again, our CNN neural network, from which we're going to call the add method, because now we're about to add a new layer, which is a fully connected layer, and which belongs still to that TF Keras layers, which I've already copied. So I can just paste that here, and this time take that tense class. Perfect. And now into some new parentheses. I'm sure you figured out what to enter as parameters. First, remember we have the units, which is the number of hidden neurons you want to have into this new fully connected layer. And since now we're actually dealing with a more complex problem, computer vision is way more complex than data mining a classic data set as before, well, we're going to choose a larger number of hidden neurons. We're going to choose 128 hidden neurons. However, if you picked the same number as before, in the previous section with our A and N, well, I'm sure that's totally fine, and I'm sure you'll get great results afterwards. But we might get a better accuracy in the end with a larger number of neurons, and therefore let's choose here units equals 128. Great. And now, second argument, that's of course the activation function. And once again, my recommendation is that as long as you haven't reached the final output layer, I recommend to use a rectifier activation function. And that's exactly what we're going to specify here with this activation parameter. And remember, the code name for the rectifier activation function is relu. All right, and perfect. This adds our fully connected layer. And finally, the step 5. You see how we're being so efficient here. In that step 5, we need to add the final output layer, which will still be fully connected to that previous hidden layer. Therefore, we're going to call once again the dance class, and therefore in the new code cell, I'm going to actually, take all this, then paste that here, and inside we'll only have to replace two things, which are the values of these two parameters. Because indeed, the number of units, the number of neurons in the final output layer is definitely not 128, but you tell me, well, it's actually, of course, 1. It's exactly the same as before. We're doing binary classification. Therefore, we only need one neuron to encode that binary class 0 or 1, or, cat or dog, and therefore we only need one neuron. And for the activation function, remember that for the output layer, it is not recommended to have a rectifier activation function, but rather a sigmoid activation function. And that's because, of course, we're doing binary classification. Otherwise, if we were doing multi-class classification, we would have, remember, a softmax activation function. But there we go. This will add a great output layer, which will optimize the result in the end. And now I have to say, once again, a huge congratulations to you, because there you go, you just built a convolutional neural network. We're done with part 2. We can already move on to part 3, training the CNN, and this will consist of course, making this brain, this artificial brain with some eyes, pretty smart to recognize cats or dogs in images. So now we deserve a good break, so make sure to recharge in good energy for the next tutorial, and as soon as you're ready, well, let's smash together part 3, training the CNN.